So I work as Autodesk's fellow, so my role within the organization in the office of the CTO is to explore emerging technologies, to explain those technologies, and to help exploit those technologies, but in a good way, to exploit them so that we can democratize these technologies in fascinating and interesting ways. I will never forget that so much. So what I'd like to explore with you today and share with you today are some of the behind-the-scenes research that we've been doing over the last couple of years within our office of the CTO. Explore how machine learning and explore how generative design, how these vast ranges of technologies are changing not only the way in which we design and make things, but our relationship with technology. And it's amazing. It's really interesting. A very fascinating way in which our very way of interacting with technology is moving from one way to another way. And so I'd like to kind of walk you through this story and illustrate how you may be relating with technologies in ways that are unexpected. So let's begin with the concept of fuel. The ways we have made our ideas real has always depended on some kind of fuel. And in the industrial age, of course, it began with coal, and coal was the fuel that led forth and brought forth and propelled our ideas to make it real. It allowed us to harness steam and steel, and it introduced a brand new civilization, didn't it? It enabled us to produce this vast range of transportation networks, telecommunication networks that would transform our civilization. And as Callan has mentioned to you today, the new fuel for our ideas is, come on, data, right? And data is the new commodity. And I'd like to really illustrate how that commodity is being propelled through the pipeline of the cloud. But you already know this because you are already taking advantage of this transformation. The cloud has transformed the way in which we live. It transforms the way in which we communicate. It transforms the way in which we relax and even travel. And so today I'd like to show how the growth of the cloud is transforming the way in which we make things and the very nature of what we make. And this change, we feel, is going to be remarkable, it's going to be stunning, and in many ways it's going to be irreversible. Okay, so what is this going to mean for you? What it's going to mean is that your designs will no longer be locked or confined into the confines of the box that sits on or underneath your desk, and the representations of your ideas themselves will no longer be static, and the products themselves that you make will no longer be static. We are in this world of moving from fixed things to very dynamic things. So as Callan has mentioned, we're now in a world where we have the potential to build things that are deeply connected and will evolve in the world. Okay, and at the very heart of this, again, as Callan has mentioned, is our ability to capture, compute, and to create. And we have these many shifts that are occurring as we transform our technologies from passive servants to active partners. That's the heart. That's the real shift that we're seeing in the world. So let's begin with generative design. So let me ask you the question, what's going to happen when design is going to be empowered with essentially limitless computation power? So one of the changes is the way in which we relate or direct. So with traditional computation, you decide what to do. You directed the computer to do something. You decide to run a simulation. You decide to engage the computer to perform certain tasks. But with abundant computing, that whole equation actually gets flipped 180 degrees. We no longer do designs by simulations based on a design. We no longer do it just during a design, but we do it to discover a design. So with generative design, and you'll be seeing this through the course of the day in other sessions, you describe the problem, you establish the goals and the constraints, and allow the computer to explore this massive problem space and solution space to come up with an ideal solution. So it does more computation than any single person is able to do, perhaps in their lifetime. This is an amazing story. This is a chair that's designed by one of our interns. She's 25 years old. By the way, it's the very first thing that she made. It was the very first chair she made, and she never used CAD software before. What she did do is she gave the tool the goals, height, weight, and so on, and the constraints, and then chose from, I'm not sure the exact number, hundreds, if not thousands of different options, and then it was milled out. It's not only creative, but it's also beautiful, and it's functional, and it's transforming the way in which we explore. So that's one way of thinking about generative design, to generate geometry, but that's just the beginning of it. Generative design can be applied to explore the needs of individuals and the needs of people. So I come from Toronto, and we are just moving into our new office next Friday when I'm back. And so we thought it would be really interesting to use generative design to maximize the productivity and the happiness within our organization. So we use generative design to feed in the forces that influence human productivity. We surveyed our employees and asked them what their preferences were, and then we evaluated the survey data against the constraints, so where the kitchens were, where the boundaries of the buildings were, what the directions were, and then we allowed the computer to generate 10,000 options, 10,000 alternatives, and the system tried to maximize outside views, minimize distractions, and then prioritize personal relationships. So the computer generated a variety of solutions, and then we found and picked the equitable solution. So we're not just pushing Lego blocks around here. We are instead allowing the computer to explore the best possible option. So what's the shift that happens here? We're moving from directing the computer to follow the tasks that we are asking it at a low level to one in which we allow the computer to adapt and explore and to analyze and discover the best possible solution. That's one of the big changes. So what about actually creating the things that we have created a digital model for? So let's look at how abundant computing can change the way in which we physically fabricate things themselves. So robots themselves kind of haven't changed very much in the decades, nor has the built environment that people have put robots into. And we still lock them up because they're heavy, they're dangerous, they're stupid, and they move very quickly, and they don't see you if you happen to be in the way. So that's very dangerous. Also, kind of part of this relationship between robots and the structure that we build them in is that we lock down our processes for making. It's this rigid way that we repeat over and over again. And because of these rigid processes, we as human beings need to accommodate the processes of robots. So what if we flipped this around? What if we applied machine learning and abundant computation towards this? So I'd like you to meet Ash. Ash is one of my favorite robots. It's one of several in our robots lab. And so she's not very different from many of the robots that we have in the world, except we don't keep her locked in a cell. We give robot Ash this clear stereo vision and the capacity to build and weld in three-dimensional space. And so she doesn't rely on us for direction, but instead she works in a closed-loop system, continually refining and refining and refining the model that she's building based on the feedback, based on what she actually can see. So as we build more flexibility into this system, we need more flexibility to understand how to work with these adaptive systems. So we created a virtual reality environment so that we can step into her world virtually. And in doing so, interact with her in creative, more human, more intuitive ways to be able to help her build the things that we want her to build. It's really an amazing experience. If any of you have tried virtual reality in this way, it's crazy to be able to interact with a robot in quite this way. So what's interesting here is that the space no longer, that the robot occupies is no longer dangerous. So by applying machine learning, we shift from rigid ways of working to much more fluid ways of working. So many of you may have are familiar, of course, with 3D printing and additive manufacturing, and many of you might know of our work that we've done with Airbus. So Airbus, the partition panel has been generatively designed, Now, what you probably don't know about this is that it was inspired by a slime mold named Fusarium. And the slime mold, Fusarium, it works by growing to connect to food sources. And it reinforces the connections that are good ones and eliminates the ones that are not so fruitful. And so to design the partition, we used an algorithm that is based on this very natural and very deep phenomena. And so when we generated the partition, we created this very complicated thing. And the challenge that we discovered was that it's really, really, really difficult to understand. You can hold it in your hands, but it's really difficult to understand where this part might fail. But a computer could. So we can do an analysis on a single part, but on the whole structure, it just becomes remarkably complex. So another shift that is occurring, which is starting to, I think, I don't know, I find this one among the most challenging to deal with, is that we are moving from a world of inspectable, where we understand each of the objects that we build, to inscrutable. What is inscrutable? It means hard to understand. The word itself is inscrutable. And so the very nature of the things that we're building, increasingly using design learning and machine learning, are becoming inscrutable. So let's just recap. So the partition here allows us to see that the value of generative design. It can be used by virtually anyone. We are democratizing this technology, and we can apply and extend this technology not for just making geometry, but understanding the behavior of people, and much, much more, as we'll soon see. So data is at the heart of this, and it's driving our design decisions. And so it's a remarkable transformation. And so one of the transformations that we're seeing is that that design is sort of becoming more like a black box. And just because something is less understandable doesn't mean it's less trustworthy, because computers now, as I'm sure you know, are way better than humans to be able to recognize faces, to detect cancer, and also to drive vehicles. The accident rate is much, much lower. And the reason for this is because computation is shifting from if-then statements to insights or intuition. So they don't run formulas, but instead they are learning from direct experience, watching in the world and becoming predictive, projective, and productive, as we like to say. So machine learning works not just by following rules, but instead by following the principles or deep understanding. So another way of thinking about it is kind of like this. If-then statements are like looking into the rear view mirror, whereas computational design and machine learning is looking outwards and forwards into the world. So philosophically, that's what it means. I'll share some practical examples in a moment. But we're moving from a world of conditional to a world of insightful. So let's revisit robotics. So how can we build more efficient ways of manufacturing? So by giving our robots vision, they have an ability to see, and they can detect our presence. By giving them machine learning, we give them the ability to learn, so they're no longer locked to our processes. And then rather than having them follow just traditional conditional methods, they're learning to work in the messiness of the human world. So this is one of the, I think, really important transformations. So I'd like you to meet another favorite robot of mine. His name is Bishop, and Bishop has been introduced to the very disorderly world of Lego blocks. So using machine learning, we taught, or in the process of teaching Bishop, to be really curious and let his intelligence evolve as he plays, kind of like a toddler, with these sticks. So like our previous robot, Ash, he's got eyes, and he also has a hand to grasp. And so he slowly is learning how to manipulate and stack these robots. Not programmed to do this explicitly, but to evolve and learn through many iterations. So he now has been able to evolve to be able to move some of this, to react to the environment, to select among complexity. But it's a slow process, as you know. So one of the interesting applications of machine learning is to separate the learning environment from the physical environment. So we created an artificial world within which Bishop can learn in. So it kind of looks like this. So we replace what he sees with his optical model with a computer-rendered model of a world. So using physics engines, be able to create a world as if with Lego blocks. And so think of this as kind of a video game in which Bishop can explore and try many, many things. So what's interesting about this is that we move from human time to computer time because computers can work in parallel. So we can, in the course of an evening, work on 4 or say 16 or 32 or 1 million different simulations in parallel. So think of a toddler experimenting. So at the beginning of the evening, it has no idea how to play with this, and then at the end of the evening has more expertise than all toddlers ever, since the beginning of time. And that's kind of what machine learning is actually allowing us to do. So as a result of this, Bishop has been able to learn very quickly, and we give them random samples, and he has enough experience to bring this into the physical world. The interesting thing about this is once Bishop knows, so does Ash and every other robot that has been networked in this. So unlike having every robot having to relearn this by themselves, it's distributed. See how it multiplies and communicates? It's a remarkable impact. And so where it gets, I think, really interesting is we can swap out Lego with, well, whatever you'd like. Chairs, stage, 3D printed logos, clothing. It doesn't matter for machine intelligence. It doesn't care. If it has enough time in a virtual world to experiment and build, it has the potential of developing insight in a way that is inscrutable and impenetrable. Wow. That's really one of the important learnings and lessons that we're understanding from this. So the shift, one way of talking about it, is that we're moving from a world of conformity to a world of variability. Okay, some examples. Maya. Anyone use Maya? Maya is a visual effects software. I was part of the Maya team many years ago, and it's insanely complicated to produce fluid effects or smoke effects. There are literally hundreds of sliders and drop-down menus and dials and so on that you need to be able to master. You can rest your career on Maya. Would it be possible to teach a computer how to use Maya? Well, in fact, that's one of the things that we've done. We've had Maya explore using machine learning what all of the different settings, the many billions of combinations, what the various type of smoke effects can be, and then show us a reference image like this one here, and the computer instantly knows how to generate the image, but as a real-time, three-dimensional interactive simulation. So apply that to the software that you're using now. Apply it to some of the complex problems that you're trying to use now. Okay, so another application is with a program of ours called Moldflow. Moldflow has a database of about 10,000 materials, and we study how those materials are actually flow and or can be used for manufacturing processes. Now, it's based on 30 years of data, and I think there's many people here who aren't 30 years old yet. So it's a crazy amount of data that we've assembled, but only 2/3 of the database, actually only 1/3 of the database is complete. 2/3 is still it's not done yet because it's such a slow, laborious process. But machine learning can help us scale and understand and test and evaluate the deep properties of these materials so that we can better simulate them and then apply them to machine learning, to a manufacturing process. So again, we're working in computer time to be able to process this. So the shift is moving from, I guess, programming, modeling, to understanding real-world performance. We're going from calculation to a deep perceived understanding of the world using sensors, and then cultivating intuition. You know what intuition is? It's that sense of whether something is right or correct. We all feel intuition based on years and years and years of experience. So that capacity, believe it or not, is now being transferred into the machine learning algorithms. And of all the technologies that I've seen, I've never seen one that's moved so quickly. We just recently finished a book called The Future of Making, and I got to tell you, at the very last couple of months of bringing it to a close, I was really scared because I'm thinking, this is changing so quickly. Every week there are 3 new major advancements, and so how are we possibly going to communicate that in a fixed static object? Let's look at how we can apply some of this technology to the world of construction. So we have now digitized some of the problems that happen in the world of construction. Here we have 27 million documented issues. This is a small portion of it. That's just probably 10,000 or so from 10 years of BIM data. And a program called IQ, which is part of BIM 360, takes machine learning and analyzes those problems for the purpose of predicting what could be a problem in the future based on capture, based on observing what is in the future. And the goal is to reduce subcontractor risk, to reduce dangerous situations, and to help superintendents to be far more productive than ever before. And one of our partners, Swinnerton Construction, used IQ to explore for several of their projects. And they began by where people were literally typing in the problem on site, and the computer would then begin analyzing the construction site. In fact, the whole construction site becomes computable, and as a result of that, we can apply machine learning. And we're now at the phase where we can apply photographs, scanning technology, and then the computer understands what are some of the issues that could be here. So for example, it took this image here and then processed it and found a problem. See the problem? It's damp underneath here. So that may mean that the window was fitted incorrectly. Okay, so the computer recognizes this. Or it looks at this photo here, what's wrong here? Some of the missing guardrails, so it's a dangerous, risky situation. People could die as a result of this. And what about something like subcontractor risk? When you work with a subcontractor, you want to know that organization's track record. So is it possible to capture that data? Yes. So I think the important lesson here is that this complex machine learning, it becomes accessible to push buttons. Think of 10 years ago when this thing called, what was it called? Oh, the iPhone was released. That was a decade ago. And since then, computation has grown orders of magnitude. In another 10 years, we're going to see the same rate of expansion, but more so. And so some of the aspects of machine learning that we've talked about previously will be pervasive. So it's a really good time now to really understand and pay attention to what this means. So instead of looking at project management from a rear view mirror, as we do previously, IQ looks forward and out into the world. That's the fundamental shift. And so we're expecting to, as we connect the world, as we capture more information of the world in real time, construction sites, even actuarial data, we'll be able to have a better computable model that you can use to better manage your projects and put people where they need to be in the right place, in the right time, in the right ways, doing the right things, reducing the inefficiencies. So rather than following a recipe, we reason through observation, kind of like what human beings do. So there's an ask, and the ask, I think, is tough when it comes to machine learning. And the ask is, in order for you to drive a self-driving car, you have to let go of the wheel. And I don't know if you've ever been in a self-driving car, but the very first time, boy, it's scary, because this thing is taking off, and you really, there's this whole issue of trust. But it worked. They work. They're remarkable. We have to let go in the same way of our traditional tools to take advantage of these next generation tools as they come on board quickly and augmenting. So you can imagine a world today where computation remains finite. It doesn't change from what it is today. And in such a world, your design will stay in the box, and our software would be delivered in a box. But we don't live in that world. We live in a world where computation is growing exponentially. In this traditional old world, these are the qualities of the software, of the tools that we have. But now imagine a world of remarkable, abundant, perhaps even infinite computation. And so in this world, we don't push finished products out into the world. We have a continual exchange and dialogue with the things that we make and that we produce. So our software then, the software then evolves and to have additional characteristics. One that is much more fluid, much more intuitive, and something that's much greater than the sum of its parts. So there's a remarkable transformation that's at play here. We're getting into a world where the tools that we are using have the capacity to deeply understand our intentions, the ideas that we're trying to build, but also the way in which we build them, and also the way in which our products are going to be used, and the way in which the products actually will be used. And the combination of that, of this exponentially growing computation, is the heart of the transformation. And it's a really exciting and I think also kind of a scary time, because it forces us to rethink our relationship with the technology, letting go of the ways in which we've kind of built our careers to brand new ways. And I think what that does is it frees us up. It frees us up to take advantage of perhaps what is most human and most valuable, which is our human ingenuity and creativity. But what we do now have is the potential of working with through our technology, a true design partner, one that's not really just good at execution, but one that's also terrific at exploration. And so we're believe that the combination of these two capabilities, the left brain and the right brain, are really going to bring out the very best in ourselves, in our companies, and also in our industries. And Autodesk, we are committed to building these technologies, and we're really excited to be able to share these with you. I really say that with you, and we look forward to continuing to go on this journey together. So with that, I believe we really can build just about anything together. Thanks for your time.